Okay, now I think I'm recording. So I'll start over. We're going to talk about chapter on nuclear chemistry, which it's an important chapter to understand the difference between a nuclear reaction and a chemical reaction, and especially the difference in energy that's available in a nuclear reaction. So um, we'll talk about part of the chapter. We're not going to do the whole thing. So nuclear chemistry. So Um, if you talk about natural nuclear processes, it's called radioactive decay. So naturally, some isotopes just aren't stable, and naturally they'll give off alpha, beta, gamma, positron, or have electron capture take place. So these are telling you what kind of particles are involved in those processes. So if you say something undergoes alpha decay, it gives off a helium atom without any electrons. Beta decay gives off an electron. And so this process of radioactivity or radioactive decay um, is a result of certain neutron and proton ratios just aren't stable. So if you look at this, this is the number of neutrons on the y-axis, protons on the x-axis. And so we're talking about that ratio. And that ratio being about 1 is stable, but you can see this blue band of stability is slightly above that, so slightly more neutrons than protons. And that makes some sense because protons are positive and they repel each other. So the neutrons you can think of as acting sort of as a buffer. And so this is just a reaction that's showing you that you can make a helium nucleus from 2 protons and 2 neutrons. In this process, you're essentially taking individual particles, protons and neutrons, and fusing them together to make a nucleus. So this is called the binding energy. So there'll be a change in energy for that process. And the equation that you'd use to calculate it is you'd look at any mass difference. So E equals mc squared, Einstein's most famous equation, is what you'd use here. And you'd look at the difference in mass between reactants and products, and that's equated to a difference in energy. So this nucleus must be lower in energy or we wouldn't have it existing in nature. So this must be a process that has a negative delta E. And because it's E equals mc squared, c is the speed of light, and that's a really big number. So that means that very small losses of mass can result in huge losses of energy. And this is showing you that if you look at per nucleon, so per proton or neutron, the most stable isotope is iron 56, and everything else is less stable. So that means you can fuse things that are on the left-hand side of that. You can make them into iron 56, or if they're on the right-hand side, they can undergo fission. They can break apart to become smaller particles and have the same mass and the same neutron and proton ratio as iron 56. So there's radioactivity, but then there's also the processes that we use to get energy. So whether you're talking about nuclear bombs or nuclear power plants, this is the primary source of that energy. So you take uranium, the 235 isotope on the left-hand side, and if you hit it with a neutron and it sticks, essentially you create a very unstable nucleus, and that undergoes fission. So it breaks apart into several other isotopes. And in that process, it also gives off more neutrons. So those neutrons can go back and then hit another uranium 235. So because there are 3 of them, this can create a bomb. You can create an exponentially increasing number of uranium 235 breaking apart. And so the energy going up and up until it's explosive. So this is just one particular fission reaction. Uranium 235 is struck by a neutron, creates barium 142, krypton 91, and 3 more neutrons. So this is a self-sustaining reaction because the products create more neutrons that can go back and be reactants. So in our power plants, we use that process, and when we are in class, we'll go through the calculation of how much energy is released in this process, and it's a lot. So that energy can be used to heat water that can then be used to create steam, turns a turbine, turns a generator and makes electricity. So that's the most common way to use nuclear reactions to make electricity is through the process of heating up water. This is just looking, and this is old, this is 2013, so there is still a lot of nuclear energy. And I would say the US is on the increase. For a long time, it was on the decrease because nuclear power plants are super expensive to build, and we still haven't figured out where to put the waste. So there are lots of issues, but because it's considered a carbon neutral source of energy, we're on the increase in terms of making more nuclear power plants. Fusion is the opposite process, so you can fuse small nuclei together to make them closer, like iron 56, more stable. And so these are some of the reactions that happen on the sun. So two protons can collide and you can create deuterium, so the second isotope of hydrogen, and a positron, or any of these other reactions. So in each case, if you think about the reason why we don't use nuclear fusion in our power plants, you have to take two protons and get them close enough together that they stick. And we know that protons repel each other, and it's not until they get to 10 to the minus 15 meters apart that the strong nuclear force takes over and you can get them fused into another nucleus. But because that takes so much energy to get them that close together, it's very, very challenging. We've been working on trying to build nuclear fusion reactors for, oh gosh, ever since I was in college, so a long, long time. And we still haven't created these kinds of power plants. On the sun, it works great because the temperatures of the sun are very high, and so that you have that kinetic energy for the particles to get close enough together. So the advantage is that the hydrogen isotopes used as fuel are cheap and plentiful, and the products are non-radioactive and non-polluting. The disadvantage is what I said, the temperature that you have to have is about 40 million Kelvin in order to get the process started, to get the nuclei close enough together so that they'll fuse. So these reactions that we've been talking about are really transmutation. They're the change from one element to another, but they're in reactions that we create. So it's not radioactive decay. It's a reaction that's created probably in a particle accelerator. So one of the isotopes that we can make is plutonium, and plutonium is a very, very dangerous element. And this particular isotope, it's chemically and radioactively one of the most toxic elements there is. So but you can make it. It's not, doesn't naturally occur. So you can make plutonium, and then that can also be used in power plants. And that is all we're going to talk about, at least in this part of the lecture. And in class, we'll go through the calculations and talk a little bit more about some of the issues with nuclear energy and some of the real advantages of how much energy you get from a very small quantity of fuel. So I'm going to stop this.